But having said that, while everyone is getting settled, I mean, I am nothing but a boring person to introduce someone who is infinitely more exciting than me. I am really honored to be introduce Staffan Truvé as our closing keynote for the Sprint 22 reporting workshop. For those of you that have not met Staffan before, which I think is really hard, Staffan is the co-founder and CTO of a company called Recorded Future, which I'm sure he will talk about, but it's viewed as one of those stars that has been growing incredibly fast and is a very successful company in its space. And I look forward to hearing more about that. Previously, he was CEO of SIX, the Swedish Institute for Computer Science. And according to Crunchbase, Staffan has founded more than a dozen high-tech startups, so maybe he can teach us a little bit about that, because clearly I have not founded as many companies as he has. So that's really exciting. Also, he has, I think, was in the board of our computer science and engineering department here at Chalmers. He is a Chalmerist, as the Swedes call it. I think he studied at Chalmers. But he is also a member of the Royal Swedish Academy of Engineering Sciences, and even caused me to become a member of that organization, for which I'm still very, very grateful. And with that, I think it's much better to let Staffan introduce himself. So Staffan, thank you so much for taking the time to take the time to present the closing keynote to us, and we leave the floor to you. So please, if you have any slides, feel free to start sharing them.
Thank you. Hi everyone. Thanks for the nice and exaggerated introduction, Jan. Yes, very glad to be here. Let me just share my screen here. If there is some strange, someone has a microphone or some strange noise. Can someone just confirm if you see my slides now?
We can see your slides.
Excellent, thank you. So when Jan asked me if I could speak, I dreamt up this title. I have a bit of a concern right now that the title is better than the talk, but I'll do my very best. So as Jan mentioned, I'm currently the CTO of Recorded Future. I've been doing that as my main thing for the last 15 years. I've never done anything in my life for such a long time. And when people ask why, I'm usually saying that, first of all, it's extremely interesting, but it's also extremely challenging. As you'll see, we're trying to solve some very hard problems, and we still haven't solved them. So it's a good reason to keep working on it. So essentially, I'll try to cover three things. I'll talk a bit about what we do at Recorded Future. Then I'll talk, what you could say, about a few success stories, especially about using machine learning. And then I'll wrap up with some fun problems we've seen in doing it. So we founded Recorded Future in 2009. We actually started thinking about this a couple of years. Our idea from the start was to build a digital twin of the world at internet scale and in real time. Over time, we've evolved to primarily focusing on building a threat-oriented digital twin. So what we try to do is we try to record everything which happens on the internet, not only what people are publishing, but actually technical details about it as well. I'll come back to that. And then we organize this information, and we don't organize it for search like Google and others, but instead we try to organize it for analytics. And when we say analytics, we think both about humans analyzing trends, anomalies, and stuff like that, but also algorithms. And I very firmly believe that when it comes to building, let's say, AI-based systems, I really think you should almost always think in terms of the machines and the humans working together. In chess, as you might know, they like to call this centaurs, when you have a great chess program working together with a good chess player. Up until AlphaZero, essentially, you know, the best chess player in the world was not an algorithm. It was actually a combination of a human and an algorithm. And in our case, it's absolutely true. We try to automate as much as we can, but we also very humble and know that at some point the analysis has to be completed by a human, typically. You could say that we use AI for two things in our systems. One is for automating tedious tasks, like reading tens or hundreds of millions of documents per day, which humans could do great, but we would end up having some while back did the estimate for probably 30,000 people having extremely boring job reading things all the day. And the other part is for augmentation, to do analytics on this data, which goes beyond human capabilities because it's too large data sets or too high dimensional data, for example. So the reason we decided at least 15 years ago that we wanted to build a system which organized the internet for analytics is, of course, that today everything runs on the internet. And since then, we've come to the conclusion that when we started off, we really saw that the internet was becoming a good reflection of the world, so that everything happening in the world got reflected on the internet, either through humans writing about it or through sensors of various kinds feeding data into the networks. The interesting and actually somewhat scary thing is that since then, I think we're also starting to see that the world is becoming a reflection of the internet. And the most catastrophic example of that, I would say, is the events at the Capitol in the US, when what started as an online movement all of a sudden turned into a real physical event. I mean, it almost looks like a video game when you see these scenes from the Capitol, but the precursors were already out there on the internet. And in general, it's an interesting thing that threats are converging. So we like to talk about three categories of threats that we are tracking. First of all, it is the classical, if you like, geopolitical or kinetic threats, as the military guys like to call it, bombs and grenades and stuff. And then, of course, you have the cyber threats, which have become an increasingly important part. And the third part is, of course, the operations, attacks on your brains, as you might. And these are all co-occurring. And nothing exemplifies that better, unfortunately, than the events in Ukraine. A good example is that the first sort of major increase in cyber attacks on Ukraine started actually on February 23rd, so one day before the physical attack started. It's interesting to note also that since then, US intelligence has reported that even Zelensky, one day before, did not think that Russia would actually launch a full-scale attack. But the signals were actually already there in terms of increased cyber attack activity. And of course, since then, you're seeing all three things playing out at the same time: propaganda, cyber attacks, and the physical attacks. So what we try to do then is to, watch over the internet to see what's happening in all these three aspects. We are, however, focusing primarily on cyber threats. And here are a couple of historic examples of what our system has discovered, almost autonomously, actually. We've seen things like, this looks very anti-China, it's just a coincidence, or maybe not. Examples of things our systems detected was a couple of years ago when we found that multiple machines owned by the Catholic Church, both in the Vatican and in Asia, were infected by Chinese malware and was reporting things back to Beijing. Similarly, at both last year and actually the beginning of this year, we found proof and good evidence that there were actually similar Chinese threats to Indian power sectors. So we found 10 power stations in India which were continuously communicating with servers in China again. And we could investigate the traffic even further and see clear signals of how it was done and so on. This was something which did not cause any harm, and that, I think, is one of the interesting and scary parts of the continuous ongoing cyber war, is that this was happening, they were infected, but nothing bad was observable. And of course, this is the typical thing which we should be most afraid of, is that we don't know how many systems out there are infected by just in silent mode. So when an actual major conflict arises, someone is able to press a button and close down the power grid or things like that. So those are the kind of things we try to help our clients by detecting. As Jan mentioned, by the way, I actually didn't put in a slide here about the company. So we founded Future Future 15 years ago. We've been very successful, grown significantly. We are today about 850 people globally, headquartered in Boston from the start. All core R&D being done in Gothenburg. In Gothenburg, we are somewhere between 110 and 120 people today, I think. And essentially all core development, both in terms of core infrastructure and the stuff I want to talk about, NLP and image analysis and so on, is done in Gothenburg. But so this is what we do. Let's move over to how we do it. So as I mentioned, the core thing we want to do is to build this thing which we like to call the intelligence graph. So the intelligence graph and our services, which we together call the Intelligence Cloud, is really the core. And it's a fundamental idea, actually, even to make this financially viable. One of our core ideas is that we wanted to build one representation of the world. We are not building any separate data sets for different customers. So all our currently about 10,000 human analysts using our systems are working on the same graph, a knowledge graph representing everything that's happening in the world. Then we do actually slice the graph and give different users access to different parts of it, depending on their use cases and so on. But it would not be financially feasible to run this business if we were not able to have one shared representation which everyone benefits from. So essentially what our system does then is collect everything. We've always had the ambition to be the hamsters of the internet, if you like. So we collect as much text as we can, everything from big media down to social media, even all the way down to criminal underground forums of different kinds. And then we actually, on top of that, add technical information, like all domains which are registered in the world, certificates which are registered, all the way down to actually collecting network traffic data, net flow data. Organize that, store it in one graph, and use it to serve everything. And this is a more sort of detailed picture of the same thing. So you could say that we essentially have 4 major categories of information flowing into our system. We started out doing text, and actually for the first almost 10 years, we did nothing but text from a lot of different sources, but essentially we did text, and then we did natural language processing to take that unstructured text into structured data. 5 years ago, we started technical. So we started subscribing to IP and domain registrations, DNS data, whois data, certificates, and things like that. And then only about a year and a half ago, we said that, well, now we've done text for a long time, but of course, everything on the internet is becoming more visual. Images are becoming more and more important, and video. You might have heard that some people call the Ukraine war for the first TikTok war, because so much of the reporting actually takes place as short video snippets. So about a year and a half ago, we started preparing for this. So we added image collection and video link collection to our system. And of course, just like with text, we're then adding analytics on top of that to make it searchable and analyzable, to be able to do trends and stuff like that. And these things interact in fun ways. So of course, we find links to text and to images in text. But actually, we also take the images, we do OCR, optical character recognition, on the images, and we find interesting little snippets of text in the image, which we then can send back to our text collection. I'll show some examples of that later on as well. So this all feeds into the graph, but the graph is actually fed in other ways as well. We do, I mean, you could say that all this whole thing is fully automated. There are no humans in the loop in terms of collecting everything from the internet and organizing it into the graph. We do actually have a team or 2 teams, you could say, of humans. We have a curation team, because even if our algorithms are pretty good, they are not perfect. There is always noise coming in and machine learning things to be doing incorrect deductions. So we have a manual curation team for fixing errors in the graph, which are caused both by incorrect information entering the system or incorrect interpretations of it. And we actually also have our own team of about 50 human analysts who are writing reports based on the data in our system, but which then also gets fed into the system. And then we do a lot of derived analytics. So we use the intelligence graph to find new things, and I'll come back to that in a second. And then this is all served out to our users. So in essence, again, our key asset is this intelligence graph. It's a pretty big graph. It contains, I mean, numbers here are very hard to comprehend, but today it consists of 2 kinds of nodes. You could say one kind is what we call entity nodes. So those are the nodes representing nouns, if you like. So there's a node in there for persons, companies, locations, products, malware, etc. And also virtual things like IP addresses and domains and so on. And then we have the other part, and we have about 8 billion of those nodes in there. Very comprehensive representation of every location in the world, and essentially everyone who's ever been mentioned on the internet is in there. And then we have what we call reference nodes, and those are, or event nodes, and those are linking the entities. So if someone, for example, would be tweeting that I hear that John Bosch is traveling to London. There will emerge, probably John will be in there already, London is definitely in there. So we have a couple of entity nodes, but when we get that tweet, we'll analyze it and we'll get a new reference, which we will call a person travel reference, which will then have different roles, so it will have John as the traveler and London as the destination. So every single thing we get like that gets represented as a new reference node. And we have today somewhere around 110, 120 billion reference nodes. So in total, you can think of this as a graph with roughly 130 billion nodes and of course several hundred billions edges. So it's a pretty big graph. So that's nothing you as a human want to sit around and watch and try to understand what's happening. So of course what we need to do is to find different ways of abstracting or making this manageable. And the first thing we do to do that is that we allow our clients, whether it's a company, an organization, or an agency, or a nation, to define lists of what they care about. So essentially, you provide lists of, for example, your employees, the locations where you're active, the suppliers and customers you have, the technologies you're using, the digital assets you have, like your IP addresses and the domains you own, everything like that. And all these lists define your digital universe. And essentially what happens when you do that is you can think of it as adding subscriptions. So you add subscriptions to all these entity nodes in the graph. And then what's going to happen is that now you will automatically notify if there are any updates to information related to those nodes. So in the perfect world, this would be to define the universe, then you essentially sort of lean back and wait until the system alerts you, for example, that there is an increased risk of cyber attacks against a certain software that you're using, or that one of your office locations is in an area where there is an increased risk of a terror attack, for example. So that's one important tool to allow clients to define their universes. But as I mentioned, that's not enough. You also need to figure out what's relevant to think about. So the other thing we do at a large scale is to do two things. First of all, as I mentioned, a single node here represents a certain entity. So for example, Nokia, the company, will be a node in the graph here. But what we actually do is we gather information related to Nokia. So we gather information automatically about who's buying and selling things to Nokia, who's talking about them, who's visiting their head offices, etc., etc. And we're also on top of that doing what we call risk scoring. So essentially for about 2 billion entities, we continuously update the risk associated with them. And that could be for a company, for a person, for a location, or for even a vulnerability affecting software, for example. And this is done by having a set of rules. So we actually have a rule-based system which computes a numeric risk score between 0 and 100. And essentially what you can then do, as I mentioned, to get alerted is that you can say, for example, here are all my suppliers. And what I want to do is get alerted when one of them gets a cyber risk score above, let's say, 60. So the risk score indicates essentially for companies how risky it is to have your systems connected to their systems, because it estimates their cyber exposure by looking at, for example, how many lost credentials can be identified, how much talk is there about cyber attacks having happened against that entity, or even in criminal forums discussion of attacking that entity and so on. So the risk score gives a nice concrete way of estimating how important this is. And then of course you trigger on that, and that allows the human analyst to go in and do a deeper interpretation of the situation. Exactly what I talked about before in terms of centaurs, so the machine does all the collection, the fundamental analysis, the computation of the risk score, and then we hand over to the human. And I think this is, maybe my sort of key message here is that I'm going to lean heavily on Daniel Kahneman and his Thinking Fast and Slow book here. If you haven't read it, you should. So what Kahneman talks about is that he thinks that in our human brains, and I would say in AI-based systems as well, there are almost always these two different systems working. He calls them system 1 and system 2. I think of system 1 as being the perception system. So that's the part which looks at the world and does fairly simple classification or categorization of things, exactly what machine learning is good at. So that builds a fundamental representation of the world. But then on top of that, there's this, what he calls system 2, the logic reasoning, or as I prefer to say, the rule-based system. And I think if you look at many different kinds of AI-based systems, they have to be organized this way. If you take autonomous cars as an example, of course you need a basic perception system, which can use cameras and lidars and whatever to build a model of what the world around the car looks like. Are there dogs or cats or other cars and things in front of the car, things like that. But then you also need a logic system to decide what you actually want to do as a car. And the reason this, I think, has to be rule-based is that in part, cars, the way cars can drive is regulated by laws. Take a good example is that, in the US, you're allowed to turn right at a red traffic light. You're not allowed to do that in Sweden. But that could change all of a sudden. And, if Sweden's laws would change so that you could turn right on a red traffic light, you can't go out and sort of rerun your cars a million kilometers to train a new model. You essentially want to do an update to the logic part of the car's system, which tells it that now you can act in a different way, but based on the same perceptual data. So I see it a bit like this. In our world, I would say that the perception part is what takes the real world and computes this knowledge graph, builds and updates the knowledge graph, which represents in an abstract way what the world looks like. And then on top of that, you can have your logic system, which can compute things like risk scores and find other things. That part as well. It's not exclusive or between these two things here. But I think to a large extent, you can think of the ML-based perception being the fundamental underlying system 1, and then you primarily use rules and logic on top of that to reason about things. And it goes back, of course, to the way we humans are. It's very hard for us to describe algorithmically how we recognize a cat. We just do it. But we can usually pretty well write down the basic rules for how you're allowed to drive a car in the street, for example. So, given this, let me dive into what we do on the perception side, and this is going to focus primarily on the analysis we do of language and images. We do have other systems as well, which works on technical data and so on, and that's done both with machine learning and rule-based systems, but I'll skip that for today. So let me start with our roots, our text understanding or natural language processing. So essentially the core of our system has always been to collect all the text from the internet, do various kinds of analytics, text-based analytics, and then go on to higher level data analytics. And when we started out, and this is sort of our general pipeline, so we get a piece of text in. First we classify it. Essentially we try to determine, is this prose, or is it maybe a log file, or is it source code, or what kind of text are we looking at? And then we go on to, if it is prose, we go on and try to detect what language is this. Is this Chinese or English or Japanese? We then dive a bit deeper and look at classifying topics. So we classify text, being, say, technical or economic or sports. One of the fun reasons that we're doing this is that actually early on when we were analyzing, we noticed that our systems, which was looking for violent text, often got confused by sports text, because if you think of it, sports referees are often very metaphorical. They talk about how they crushed the other team and they launched an attack in the second inning, I don't know what. So what we use the topic classification for is actually to drive downstream which kind of other things we want to look for. Then we do entity recognition. So that's the part where we find the nouns, the person or the location or the malware. We do event classification, as I described before. We can identify person travels or cyber attacks or terror incidents, a whole slew of different kinds of events. We do the role assignment, where we see which different entities are taking what roles in that event. Then we do something which we call temporal analysis, where we look at the publication date of a text and temporal references in the text. So someone publishes something today and says, next Thursday I will be traveling to Paris. Then that will be classified as a travel event, but the date of it, the event time, will actually be next Thursday, whatever date that is. And finally, we do sentiment analysis, to look if the text is positive or negative or violent. We have a whole slew of different kinds of things. So from the start, you have to sort of look back and see that we started building the system before the days of deep learning. So some of these components, like the left ones, classification, text, language, and topic classification, they have always been machine learning based. It's sort of a natural thing. Same thing for sentiment analysis. But the middle part, the event classification, role assignment, and temper analysis, when we started doing that, that was primarily classic linguistics. So essentially what we did was we had a parser which could handle maybe 10 different languages at that time. We could parse the text into a parse tree, and we did, for entity recognition, a combination of rule and machine learning based actually. But then we had a system which reasoned over the parse tree to decide which roles we had, who was the driver, who was the attacker, and so forth. What's happened, thanks to the revolution, I would say, in text analytics using machine learning, is that middle part of the system is today primarily becoming machine learning based. And we are currently, I would say, at our third generation. We started doing some, say, old school machine learning here. But the big difference has really been what's happened over the last few years in terms of transformer models. So, you all heard about BERT and GPT-3 and the others. This is actually the first time where I would say machine learning actually allows us to develop these systems in a more efficient way. When we did the first round of machine learning based event classification, for example, we had to spend so much time collecting data and annotating data to train the models that we did not gain anything in terms of data development or in the end actually quality of the classifiers. But what's happened now is that with the emergence of the transformer models, and you get these pre-trained language models, things have changed dramatically. So a couple of years ago, we developed our first BERT-based model, which we call TerrorBERT. So that's based on taking an off-the-shelf BERT language model and then adding a new head end for it, trained on terror data. So we still have to provide training data, we still have to annotate text and so on. But the big difference is really that since the language off the shelf has a much better general understanding of language, we need less data to train it, and performance becomes significantly better than what we were getting in previous generations. So we started doing that. These days we're only doing transformer-based models, and we're using BERT or Roberta for almost everything. So when we, about a year and a half ago, started to add another language, Korean, to our system, we decided to, from the start, only use that. Again, we were able to take an off-the-shelf pre-trained Korean BERT model. In this particular example, we had to annotate about 37,000 sentences related to cyber-related data, but we got a really good precision of 85% out of that model. We would, if you look at it comparatively, we would have spent much more time and money building a rule-based system than what we needed to do here. So this is, of course, very exciting. So this has helped us reduce the time to add new event detectors in multiple languages. But I think this is really just the first step of this. And the most significant next step here, because if you think of it, as I said, we want to cover multiple languages. Today we cover 14 different languages, and we have maybe 20 event types which we focus on. And of course, that becomes a big matrix where you need to train a model for every language, for every event type. But one of the more exciting things happening now is that we started exploring multilingual models. The first example we did was this. Excuse me. So in this case, what we did was we took an existing model which had been trained on both English and Japanese. And what we did was we added training data, a label data set, only in English for cyber event data in this case again. And the magic thing is that the new trained model there, when we tested it on Japanese data, it actually got extremely good performance on the Japanese test data, even though it had never seen any Japanese training data. So I think this is becoming the next big thing here is really the multilingual models and the fact that you can then train in one language, but you can actually get performance out of it in multiple languages. So that's extremely exciting, as I see it. And I think this is going to keep us busy for a few years now, probably, just moving all our systems into this way of building event detectors. I hate these sequential things. So what we're doing now is we're doing exactly the same thing. As I mentioned, we started a year and a half ago collecting images. And essentially, we're building a similar analytics pipeline for images. In a pretty similar way, you can say we start by some broad classifiers, like we've built systems for detecting things like military imagery. And what you can do then is that you can take those images which you detect as military, and then you can put more refined classifiers on that. So essentially, when you talk about entity detection in text, you can do the same thing in images, but you like to call it object detection then. So you could actually then have an object detector, which is like the entity detector for text, which finds tanks in this example in images. And then you can have a third level where you actually look at those identified tanks, and you can have a more precise classifier of tanks, which actually allows you to identify what brand or which model of tank it is. And I think this highlights what I've become starting to see more and more as a general mechanism for how perception is done. And this is actually fun because this goes way back in the early 90s when I did my PhD work. I was actually working on image analysis, and I was working in the field called natural computation, where we try to be inspired by biological systems, ways of doing things, and then using that as guidance for how to build digital systems. And I think what we're seeing here is called now a perception funnel. I have a strong belief that this is exactly how biological beings work as well. So what you want to do is you want to allocate your resources in the best possible way. And that means that for perception, what you want to do is have, first of all, very cheap classifiers, which gives you a rough idea about what's in the image. And you can think back to the text example where I said that we started off by classifying which kind of text it was. Same thing here. What we're doing in this example here is that we're today collecting about 500,000 unique images every day. What we have is we have a very cheap classifier, which we run on all these images, which is, you could say, a coarse classifier of are there aircrafts in this image. That actually reduces the number of images down from 500,000 to about only 2,000 per day. And then for that smaller set, you can invest more in other kinds of detection. So you can do aircraft object detection, finding the boundary boxes of the aircraft, and you can even throw on an aircraft type classifier, which can do the entity detection and tell you what's in the image here. And I think this is an interesting thing for all perceptive systems to think about. How can you build this kind of funnel? Starting off with cheap classifiers, which you can afford to run on a huge data set, and then funnel it down to more expensive, more precise classifiers, which you can use to run on those smaller sets. Because when you're starting to do things at internet scale, you always have to think of cost. And this way of reducing cost by doing cheap things at large scale and expensive things at a smaller scale is really key. Another example of how we do this is we have a classifier now which looks at images and detects if there are protests. It's, I wouldn't say super cheap classifier, but reasonably okay. And what we do is that once we have identified images which contain protests, we can throw on another model which actually uses the image to do location. So essentially what we're using there is a system, it's an off-the-shelf system, which can find things like landmark buildings in images. It's pretty expensive. We wouldn't be able to run that on every single image we collect. But now we only run it on protests images, and that's a small enough set that it's feasible. And of course, it turns out that an interesting side note here is that the fact that a lot of the protests in the world are actually happening close to landmark buildings, because you want to protest outside of parliament or outside of a hospital or whatever. So in combination, this actually gives us both good protest detection and automatic location detection of an image. So now those were some sunny stories about things that work well. But back to the trenches then, I thought I would wrap up by giving a couple of examples of some of the challenges we see. And of course, you know, it's all, I won't say too much about all the general stuff, you know, for machine learning, the fact that you have to spend a lot of time on collecting a balanced training data set. You have to watch out for and measure if there's bias in that set. When it comes to language, it's an interesting thing, you know, language evolves. It doesn't evolve extremely quickly, but quick enough that if you're building a system like this, you're never done. You continuously have to monitor your models and see if there are new ways people are talking about certain kinds of events, for example. So we found out that, you know, even years after we launched the model and we've improved performance, we still routinely do sampling of the data, and we have human annotators who go in and check that our algorithms actually do detect things in the right way. And as usual, primarily we use this to keep track of precision. It's always much harder to keep track of recall, of course, because what you don't see, you don't see. But we do try to estimate that as well. But let me give you 3 examples of fun problems. The first one is this, which I call the German Christmas market effect. And what this is really is an example of that. You think you've built a good classifier for something. In this particular case, we built a classifier to detect terror events, and we noticed that it was doing a good job. Actually, had very good performance and recall numbers. But what we noted after a while was that everything which mentioned a Christmas market in Germany got classified as a terror event. So we went back and looked at our data, and the thing was that I would say general news in general doesn't report a lot on German Christmas markets. But as you might recall, a couple of years ago, there were a number of terror events happening. And this is, of course, the typical thing for machine learning, that the algorithms don't lie. They looked at the data. They saw that every time there was a Christmas market mentioned in Germany, there was a terror event associated with it. So, of course, the model learned that. We have similar things. We noticed on our cyber attack detector that whenever we saw North Korea and Sony mentioned together, it got labeled as a cyber attack. Same thing there. No one in the world had talked about North Korea and Sony without mentioning the cyber attacks which North Korean hackers launched on Sony some years back. And of course, you could say that this is a kind of bias, but really it's very, very hard to monitor for this automatically, to see these kind of correlations which the algorithms are so good at learning, and which really requires a whole different level of understanding of how the world works before it's actually going to be there. So this is something which we've only figured out ways of detecting by monitoring data, and of course using feedback from our users. You know, when they started pointing this out, we quickly saw the problem and we could fix it. But this kind of things about sort of asymmetries in the world, I think, is an interesting challenge. Another challenge which we fought a lot with is what you could call the different sides of the story, or, you know, one man's terrorist is another man's hero. I took an example here from one of the oldest running conflicts in the world between Israel and Palestine. So as I said, we do very broad collection of sources from all over the world and so on. But for an event type like this, like something, you know, some clash between Israeli forces and Palestinians, that's going to be classified as a heroic event in maybe Palestinian or pro-Palestinian media, whereas in Israeli media, you know, those are Palestinian terrorists. So this is an example where, again, we don't have a good solution to this. You know, in a way, you could say that we're okay because we are actually classifying, in this case, what we call armed assault events. So clashes between humans which involves violence of some kind, and that's detectable irrespective of that. But actually, you know, if you want to detect more who's the attacker, who's the target, and if you want to have sentiment towards other things, it's not so that there is some objective truth out in the text step. You really have to into account which viewpoint you have. So that's another interesting challenge, and of course you can find that in many other kinds of reportings as well. The third one, which I wanted to highlight, this one I think is great because this one took us quite a while to discover, and one of my colleagues, Catherine Caffey, has given this a great name. She calls it horizon frustration. What this is that very often the kind of events we're looking for are fairly rare. So it means that we don't have a lot of data to annotate, which is actually talking about it. And what she's noticed and what we've noticed is that as you give data to annotators, and you tell them that you're now annotating this data and you're looking for, let's say, terror events, for example. What happens is that they start looking at text and they essentially only see negative examples. And they know that they are being paid to annotate for positive examples as well. What happens is that after a while they get tired and bored. And what happens is that their neural networks, if you like, their brains start getting affected. So after a while, they will start thinking differently. Essentially, what happens is that they will start looking at text in a slightly different way, so that they will start thinking, well, this is almost a terror event. It's what we call a near positive. And eventually what's going to happen is that your data set will be polluted because you will get all these near positives annotated as positives, essentially because the annotators got tired. Of course, you can solve this in different ways by rotating the data, having many annotators and so on. But I think it's an interesting example of, again, that there is no objective truth, and the annotator's psychology actually affects you as well when you're trying to do this. So to sort of wrap up here, I think, first of all, my conclusion is that when we're building these kind of systems, I would say almost always need to think in terms of systems 1 and 2, perception and then logic, or maybe feedback loops in that. I think this notion of having a perception funnel is important if you want to do this at very large scale. That becomes the efficient economic way of doing it. As I mentioned, transformer models have been real game changers, but there are no silver bullets. There's still challenges in doing that in terms of annotating data. And I think for whatever domain you're in, you need to be aware of, what I call these data traps. That concludes with my favorite slide. The best way to predict the future is to invent it, and that's what we try to do at Recording Future. Thank you.
Well, so for everyone online, feel free to put questions in the chat. But I had one thought when I was thinking about adversarial networks and GANs and stuff. How hard or how easy is it for me to start generating data that will make it more difficult for you to identify the kinds of events that you're looking for? That must be something that you at Recorded Future have looked into. So can I start to generate stuff just to confuse your systems?
Yeah, and it's interesting. It's a very good question, and it's a version of a question I get very often. What happens if people lie on the internet? If you like.
I mean, I lie all the time, just for the record.
Yeah.
So
No, but we took a very early on a decision and said that we want to objectively report about what's being talked about on the internet.
Yeah.
So that means that if someone publishes something saying that Margareta Andersson got shot today, for example,
yeah.
Even if our system knew that was fake, we still want to report about it. So it's a great example of where we actually, we would build a representation of an armed assault event for that kind of thing.
Yeah.
And we would alert it, and then it would, in this case, be up to a human analyst to look at that, maybe check with secondary data and try to validate or falsify it.
Yeah, yeah.
I think this makes sense, but of course it's becoming harder and harder. So good example is, people who are doing, of course, deep fakes with both imagery and video now.
Yeah, exactly.
And we don't do any deep fake detection in our system today, but we are actually prototyping that together with some partners now.
Right.
Because that's a good example where you cannot expect the human analysts to be able to determine this.
Yeah.
I do think it's useful to have automatic detection so we can flag it. And of course, it's super interesting. It's more interesting to see that there's a deep fake video about an event than if it's a real video, because that's an incident which you want to track.
Yes.
So you could almost say that lies are more interesting than the real thing.
Yeah. I had another question, but there is a question in the chat by Marie Welmer, who asks that I assume that your solution would require a massive amount of storage and computing power. Can you elaborate a bit on how you handle that? Do you use
Yes.
computers, Staffan, or is it just us?
We pay a lot of money to Amazon. Is the quick answer. No, but it's quite true. You know, so on a serious note, you know, this graph, we actually use Elastic to represent the graph, which is a bit unconventional. You know, but there is no graph database in the world which scales to a graph this size. So we're actually using what's really a text-based system to represent this. But our indices for representing the graph are running on something, I think, you know, maybe let's say 8,000 to 10,000 very expensive servers. So it is expensive.
Yeah.
You know, I think we were lucky when we started. We started at a very good time. So we've been running our systems cloud-based from the very start.
Right.
And we make tremendous use about the elasticity of the cloud, especially if you look at the processing side of new data coming in, because that varies a lot. You know, very little actually happens on the internet on Sunday mornings. It turns out Tuesday before lunch, US East Coast time, is the high tide of information. But the whole processing pipeline scales very nicely horizontally and automatically based on the inflow of data.
Right, right. But I suspect that your bill for that Amazon sends you every month is not a pretty one, to say the least.
No, you're quite right. Our CFO is not happy.
No,
I think it's you know, I have to. It's interesting side note here that for reasons which we don't understand, our graph has typically been doubling in size every 18 months. You know, so it's a fun thing that it's tracking Moore's law in a good way. You know, we still spend a lot more money than we did previously. I think of the, you know, the still ongoing effects on Moore's law, combined with improved algorithms and so on, has actually managed us to keep growing like this, you know, at reasonable cost at least.
Yeah. No, okay. I'm happy to hear that. I heard you talk this time and a previous presentation that I heard you give on the difference between the machine learning and using that for perception, so fast thinking, and then the slow thinking and the rule-based approaches. And that I found a very interesting stage in many contexts, because everyone is basically singing the praises of deep learning and machine learning and all kinds of other approaches, and not so many people talk about the other approaches that we have within AI. And can you expand a little bit on? And then you mentioned that transformer networks really provide some of the benefits that come with deep learning, which might be applicable to also more of the reasoning tasks. So do you see that the reasoning bit is going away after all, and we're just going to take the deep learning approaches also into the tasks for which we now would need logic? Or do you see that, where do you see the future going on that front?
I mean, I think, you know, in the end, you know, any system which sort of, let's call it, interacts with society, if you like, I think will always have a sort of rule-based, you know, because it's the law, or it's the business rules of a company.
Right.
And you know, even if it were feasible, it would be completely ridiculous to try to sort of generate training data, you know, to teach a deep learning algorithm the business rules of a company or the laws of Sweden. Yeah. So I, you know, for the foreseeable future, I absolutely think that you will have a combination of these two things here.
Yeah. Well, I mean, as a counter argument, and then we're going to wrap up, there's one more question. I mean, you know, we have traffic laws in this country, and no one in their right mind who actually drives a car will follow all of them all the time. I mean, we are, and my problem with autonomous drive is that most people do not follow, or that those systems are too logic-based. Sorry, go ahead, Staffan. I interrupted you.
I was going to say, and that's why it's so boring to drive in an autonomous car, right?
Yes, exactly. That's the point I was trying to make, but let's not go there. There's one more question, and then we're going to wrap this up, because you've been extremely generous with your time. The word GDPR is brought up in a question in the chat by Rasmus Engholm. Is that a concern for Recorded Future, or you only operate outside Europe and you don't have any concerns with GDPR?
No, I mean, we have lots of customers in Europe, so we care about GDPR, and, you know, there are California laws which are quite similar.
Yes, exactly. Yeah.
So no. So it's a relevant question. You know, my standard answer to customers is that our expensive U.S. lawyers say that we comply fully with all GDPR rules. That's one way of phrasing it. But I think it's important. So first of all, you know, we've implemented the right to be forgotten in our systems and so on, all these things. Right. But in general, you know, personal information, yes, our system does record personal information, but it does not do it to I mean, the use cases are not related to tracking individuals.
Yeah.
It's you know, we were interested in threats against organizations, but they are typically more on a higher level in terms of trends. You know, let's say on the cyber side, many hackers and so on. I would say the places where we do go beyond or have GDPR is, for example, the fact that we are collecting things from criminal forums and gathering identities there, for example.
Yeah.
But to be very frank, we are fine with tracking criminals in that sense.
Yeah, and no, I can see where you're coming from.
We take this very seriously. You know, so you know, as you said, we are a US-based entity. We've actually, when it comes to our data collection and everything, we have had very, very deep discussions with Department of Justice in the US to ensure that all the collection and analysis we do is allowed.
Right.
But you know, there can be local varieties. But you know, we are, as I said, we have a lot of very GDPR conscious customers in Europe, so they at least have agreed with us that what we do is okay.
Good. Yeah. Staffan, sorry for ending this on one of those legal notes. I mean, I am, every time I hear you speak, blown away with the technology that you and the company have built up over the last years. And as you know, your head of data science goes to the same gym as I do, so we get to chat from time to time. I would like to end this by thanking you once again on behalf of everyone in Software Center for taking the time to give us this wonderful keynote. I really appreciate it. And I hope that we can soon meet again in person, maybe at an EVA event. Sorry, you were frozen for a little bit. Your internet seems to be a little funky.
Yeah.
But with that, Staffan, you didn't hear me thanking you, but I just did thank you. So thank you very much for taking the time. I really appreciate it. And I hope we have a chance to soon exchange some thoughts again. So thank you and have a wonderful day.
Thanks for having me. Bye-bye.
Okay, take care. Bye-bye.